Hello and welcome to ninth lecture of course on data-enabled tribological engineering from experiments to predictive models. Topic of this lecture is hydrodynamic lubrication theory. First question comes, what is the really relation of hydrodynamic lubrication theory to our course or maybe with the earlier lecture where we have capped on the ninth number lecture after giving 8 lectures on other topics. So that's had been addressed in this slide. We say hydrodynamic lubrication theory relation or relationship with earlier lectures. First thing which we have learned is something lubrication, which is also common hydrodynamic lubrication. With what we say, the lubrication is a critical in keeping a machine working efficiently, and we knew that friction losses really cause a lot of economic losses, and we need to improve efficiency, reduce friction losses so that overall economic growth happens based on a mechanical engineering, based on a scientific understanding. Another one is that to prevent what we have learned, to prevent material from wearing down, because we have learned also that almost 70% failures happen because of the surface degradation, and wear really plays a very dominant role in surface degradation. So to avoid surface degradation, we need to add a lubricant layer to all tribo interfaces. We have already learned the tribo interfaces. So adding a lubricant layer to all tribo interfaces. Now it is very critical for us to understand. Now question comes, how and why lubricant layer has been talked. We already have covered when we show the ones figure from literature. The coefficient of friction varies from 0.1 to 1 and maybe even more than that, like a gold and gold, nickel and nickel will be higher values. But these coefficient of friction are under dry condition without lubricant, and it was mentioned that coefficient of friction for partial lubrication means there is a some layer on the interface or at the interface. Coefficient of friction decreases by 1/10. That means coefficient of friction here 0.1 to 1, while in this situation it will turn out to be 0.01 to 0.1. That means if I go ahead with the partial lubrication, I can add here 0.01 and zero point 0.1. Now if I go ahead with the full hydrodynamic lubrication mechanism, then I can say it is varying starting from 0.001 to 0.01. That means if you want to reduce the coefficient of friction to 100, that means 1%, we should go ahead with hydrodynamic lubrication. That's what initial literature or maybe say initial thinking says in this manner. There is a need to understand it. And one more thing was mentioned in earlier lecture, lubricant flow behavior is generally defined by Reynolds equation, and this Reynolds equation will be covered in lecture 9th and 10th. So that's why we are bringing this topic hydrodynamic lubrication as a topic for the lecture 9th. And with more thing was mentioned that it is only for the conforming contact, conformal contact. When we go for counter conformal contact, or we go with a rolling element bearing gears and all, then we will be covering that in lecture 11, that is elasto-hydrodynamic lubrication mechanism. We also learn something like a coefficient of friction is a summation of first term and second term. Here the alpha is a kind of multiplication factor, value varies from 0 to 1. Coefficient of friction, this alpha will be 0 if there is only metal to metal contact and then there is no lubrication. That means 100% friction will be because of the metal to metal contact. While if alpha is 0.7, 0.8, 0.9, maybe 0.95, then coefficient of friction will be dominated by first term. However, it is very clear that SL or shear strength of liquid will be far lesser than SM, metal shear strength. So we need to give emphasis that alpha should be as high as much possible, maybe say equal to 1. So that's what we really required lubrication mechanism or hydrodynamic lubrication for that purpose. We also understood from previous lectures that when we are talking about the mu, we can think about the physical adsorption. Reason being, physical adsorption is helping surface to glide, and in the situation Sm will be replaced with Sb. That means shear strength of boundary lubricant. Again, Sb is far lesser than Sm. That means in this situation, if we are able to do that, that will be very good. And in the situation that will be called as a mixed lubrication, wherever there is asperity, we will have a boundary layer, and wherever there is no asperity, there will be liquid lubricant layer, and then it will be mixture of these two, and its coefficient of friction will come down significantly. So that is the very intention behind this. And we also learn that because this boundary lubricant layer is providing easy gliding, easy shearing, then there is a possibility the whole layer of this molecule can be moved away from a surface, it can be removed from a surface. So that's why one lubricant layer or one boundary lubricant layer may not be sufficient, not even 9 layer, and then one report says it should be 53. However, it depends what kind of molecular layer we are using. If the length is much bigger or much longer, quite possible we require lesser number of layers. Another thing is that if molecular attraction is on higher side, again we require lesser number. If metal which has a good affinity towards molecules, then we require a lesser number of these molecular layers. So this 53 is a kind of subjective number. It can vary from one interface to other interface. So we don't want to stick to the 53 as a kind of magic number. No, it is just an illustration to mention that one layer may not be sufficient. We require many more layers compared to one boundary lubricant layer. That's what we have understood. One more thing which we have learned is something like this curve, and that says that under the hydrodynamic lubrication also coefficient of friction will increase. That has been shown in this case. And then what we also have learned, there is a Sommerfeld number. What is that? Is a RPM, shaft velocity, and then viscosity and bearing pressure. If the shaft velocity increases, the movement will go to this side. If viscosity of oil increases, again move will be in this direction. If the load increases, then movement will be opposite side. Again, whenever there is a shaft and there is a bearing, shaft will not have immediately 6000 rpm speed. Naturally, it will start always from a 0. And in that situation, the shaft and bearing arrangement or even hydrodynamic lubrication mechanism need to go through this context. That means there is an initial contact, and then maybe after few rotation, shaft is levitated and the separation happens. So that for that purpose, that's why we say the boundary lubricant layer or boundary additives must be mixed with a lubricant which is used for, which will be required for the hydrodynamic lubrication. So in short, we can say there will be always a base oil which can be used for the lubricant purpose plus additive package. If we don't have additive package, we say that maybe have a more wear, maybe have a more friction at the beginning and the ending. Just to avoid that, at least we require this one. And of course, if there is a temperature is on higher side, again base oil may be getting thinner, or we say that viscosity will be lost. Again, we may require some sort of additive. That's what we use a word viscosity index improver. That is really required. So in reality, lubricant has to be always something like a base oil plus additives if we are talking about the liquid lubricant. Of course, we have a solid lubricant, we have a coating, which will be covered in lecture 12 and 14 subsequent to this kind of lectures. Now, this is where we have shown here that if we don't take care of properly and then operating speed comes something here, or maybe say operating parameter, the coefficient of friction is far higher compared to this, so that should be avoided. That means we really require a good modeling. We really require a good quantification to come up what is really required. We require a low coefficient of friction, but for that purpose, which kind of lubricant really will have, and how much lubricant flow rate should be provided. These are the important aspects. That's why we require hydrodynamic lubrication mechanism to be covered. So what we say, another word, to improve understanding and prediction of lubrication performance or performance of lubricant in different turbo systems. It can be cam follower, it can be gears, it can be rolling element bearing, it can be journal bearing, it can be thrust bearing, whatever. So that's why we are saying various turbo systems. It is necessary to understand data enabled hydrodynamic lubrication. Now this is a new term we are bringing here, the data enabled hydrodynamic lubrication. Reason being, there are many data available in literature. People have used, or they have researched, they have experimented extensively on hydrodynamic lubrication. So we have enormous number of data available. Let's take an example here. What I have given a mention here, a Tribology handbook, which is the second edition, and MJ Neil wrote this book, or maybe say edited this book, and we can download this book also from a website. It is openly available, and this publication date is 2001. So we have a free accessibility to this. So we can get a number of tribology and data using this kind of handbook. Their data doesn't mean only the numer or numbers. Any figure which is given, it is data for me. Any picture which has been given as a debris is a data for me. So I'm talking is a graph, figures, data in tabular form, even in some, there are some sort of relations are also established, suppose, and then we want to generate a data for our own convenience purpose, that is also possible. So enough data are available, and we need to jot down, and we need to really think how to utilize in a best manner those data, so the further improvement can be achieved to minimize wear, to minimize friction, and get more and more reliable setups or type of systems. So initially I'm just referring to the pages of Neil's book, which in one book, particularly when you do surfing, in this case I surfed something like hydrodynamic, and I got 2 pages from Neil handbook, something like this. Now in this handbook particularly, he has given a suggestion, how do we optimize, how do we choose a right bearing for the operating condition. And of course he has mentioned something like a rubbing bearing, plain bearing with a porous metal that has some sort of lubricant in that, rolling element bearing, and full plumb plain bearing also. Coming to the thrust bearing, they have rubbing bearing, they have oil impregnated porous bearing, they have hydrodynamic bearing, rolling element bearing, and one more bearing he has mentioned about hydrostatic bearing also. So these are the data available. Now in this situation, whatever the load has been given to us, whatever the operating condition has been given to us, then we can choose a bearing from this. So this data can be used or can be utilized as an initial guess for us. Of course, when you go and do a literature review, people have developed a complete software on this selection of the bearing also. So that can be also treated as a data generation source for us. Now let's take an example. Now suppose the operating speed is something like 6000 rpm, and if I convert rpm to the rps, we find 100. So I have use a vertical line over here. Then we have 1000 Newton applied load, and we want to know which bearing will be better option for us. So in this case, if you look at there is a one line here, other line here, and this indicates that the rolling element bearing will be a good option, particularly if the diameter is from 10 mm to 25 mm. And same thing happens related to the hydrodynamic bearing. If you find in this case, again this is a hydrodynamic bearing, and this is a hydrodynamic bearing, and this is a hydrodynamic bearing option. Now here it says very clearly, again the diameter 10 mm to 25 mm. However, more close match comes from a hydrodynamic bearing particularly when there is a 6000 RPM. Of course, if your RPM is a lesser, naturally the choice will go to rolling element bearing. If we do the similar kind of exercise, particularly for the next curve, that is the thrust bearing curve, you can see here again we are choosing 6000 RPM, and here we are choosing 1000 Newton loads. And what we get, another thing, the diameter for rolling element bearing, it varies from 10 mm to 20 mm. And then for the hydrodynamic bearing, in this situation, it also varies in this manner. There is a 20 mm here, and this is a 10 mm here, right. So 10 to 20 mm, there is a some shaft diameter maybe can be interpolated. If shaft diameter is already given, or maybe say um, other dimension have been already given, or even you will find this kind of curve for the oil selection also, and then even the seals also. So there is enough data available, and we should utilize, and we can really take this data for the second half of the course. Initially we are trying to search what are the relation available, what are the data available, what are the concepts, and how do we really think in a proper way, so the supervised learning happens in a much better manner. Because in this course we are going to learn the machine learning, emphasis will be given on supervised learning, and for supervised learning we really require a good data, we require some relation which can be improved, and that's why many times we use the word reinforcement learning. So reinforcement learning also can be a part of our course. Now let's start again from hydrodynamic lubrication theory, and it started from a Towers test experiment. He used a partial arc bearing, and this has been mentioned here, and he mentioned that if the shaft rotates, they were able to observe the lubricant which is coming out from this hole. If it is coming out from this hole, naturally there is a pressure generation, and there is some clearance also in this case. How the clearance has been developed there or really started, even we know that whole load will be and the shaft will be here, and the complete load will come and the clearance should be zero. At least at this point, clearance should not be there, but there is a clearance. Naturally, that there is because of the shaft rotation, there is some sort of pressure generation, and that is trying to separate this surface from this surface. So that was the major reason for developing Reynolds equation. And when another point comes, that if we keep a bearing, now in this case we are also keeping a shaft and bearing clearance, there is a bearing in the shaft which gets inserted into that, they will have some clearance. And I have shown over here that if clearance increases, load carrying capacity decreases. If clearance is almost negligible, load carrying capacity is huge. That's the way the maybe when they started this experiment, they found that even though initially there's no clearance, after that there is some sort of separation occurs. So the clearance really matters a lot, or another word, we say that radial clearance which we provide to the bearing is very sensitive parameter, and we need to learn this. Whenever we are trying to use a machine learning, we need to know which parameters are very sensitive and which parameter are not sensitive and that can be neglected. So if I have a 9 parameters and 5 parameters are sensitive and 4 parameters, they do not really in fact affect much. So these 5 parameters really affect overall performance by 98%. These 4 parameters are affecting only 2% remaining. So I may neglect this because we don't have to waste time on these 4 parameters. Now again, that may depends on situation to situation. Quite possible in one situation out of 4, one parameter becomes more significant. So we need to analyze. It's not that once we have analyzed, we say no, these 5 parameters are more important, other 4 parameters are not important, we will neglect. Quite possible in other situation, slightly different situation, again instead of 5, 6 parameter become more important, then we need to consider. So we should not neglect at the beginning itself. We should account all the factors, we should account contribution of each factor, and then by eliminatory analysis we can find out which parameters are more effective. And that's why many times we use the word feature selection. If features are more important, I will consider in my algorithm. If they are not very important, I may reject it. further when we are going for the deep learning or sophisticated analysis, we may reject those things. And now here the why we have shown this figure, reason being the bearing has worn out to some extent, and as the bearing wears out, naturally clearance will increase. If clearance increases, load carrying capacity decreases. That means if I have a given initially load carrying capacity requirement of 1000 Newton, and quite possible after the bearing wear out, load carrying capacity comes down to the 800 Newton, further wear out it then comes up to 600 Newton. So this is a really continuous thing, and finally we need to change a bearing. Now if when it is shifting from 1000 to itself a 950 Newton, and if we realize something is wrong and we take a corrective action, quite possible we may not reach to this situation at all, and we can do a remedial action well before this kind of situation arises. So this is why it is really important to understand the concepts and what is available in literature, and we do a remedial action well in advance. So that's why this whole course is to really go ahead with a better and better maintenance, and come up with a better and better solution which can think about the sustainability, because we don't want any wear out, because we know very well that if material degrades we need to reject it, and whenever the material is rejected, thrown or waste, naturally sustainability issues come in a big way. Similarly, if the friction is on higher side and energy loss is on higher side, again sustainability comes into picture. So we want to minimize these two, and that's why we are trying to learn the concept in a much deeper manner. Let's see what are the pressure generation mechanisms, because in previous slide we say that Towers did experiment and then found that there is a pressure generation. What are those mechanisms? First mechanism comes to something like a converging wedge, and we say if there is a converging wedge, then it will generate a pressure. Here we are trying to show in a different manner, colorful, while here I have shown with some sort of a sketch, and shown very wedge very clearly. Here the film thickness is on the higher side, here the film thickness is on the smaller line, or another word we say the H2 is a lesser than H1, that's why there is a wedge. In this situation, because of the wedge, there will be pressure generation. How will explain those things? There is another term what we call a squeeze film lubrication. An interesting thing is that this is the most common in engine bearings, even piston rings also. Now here what we are saying, if there is a dynamic load or there is a dynamic suppression, that means one surface keeps coming, yellow surface keep coming near to the red surface and moving up again, and frequencies on higher side, it will be very helpful. Many times people feel that, oh, this is the fatigue loading and the overall capacity will reduce. No, it will may double also. So this is important, that we need to really get into this kind of thing and then understand how squeeze film lubrication is really helping in a bigger way. Now here again, two surfaces are completely separated, and often people say that when the two surfaces are completely separated by lubricant layer, it is a hydrodynamic lubrication. However, we know it is a squeeze film lubrication, but again the two surfaces are completely separated by lubricant layer. Third mechanism in this case is the hydrostatic lubrication, where we need to pump, we need to really pump lubricant at a higher pressure compared to environmental pressure, and it goes and levitate the yellow surface. This is a hydrostatic lubrication. Now coming to the why we are talking about hydrostatic, because in previous one of the slide we mentioned about hydrostatic bearing. The second thing is that how will we bring the lubricant in a hydrodynamic lubrication mechanism? There should be some way, from some place it should come. That's why we many times we use pumping mechanism. Of course, when we use for a hydrodynamic lubrication, it can be 1.2 bar or maybe say slightly above atmospheric pressure. When we come to the hydrostatic bearing, it can be even 10 bar to 100 bars also. There's a possibility. So this is the difference, but again we are bringing some pressure from outside. So whenever we do a numerical solution, this boundary condition, this pressure condition must be added. If you don't add, naturally we will be getting very wrong solution. Of course, more detail about all this has been covered in my book, which is Fundamentals of Engineering Tribology with Application. I have given complete explanation of each term and how it will be useful. Now, this figure I have picked up from a literature. This indicates when initially the shaft and the sleeve, they touch each other at the bottom. Now, when the rotation starts, as the rotation starts, lubricant which is filled in this clearance space tries to retard the shaft motion, and that's why the shaft the position is changing from a vertical this side to this side. Now, with a little more velocity and direction, then it shifts to this side. So, first is both the centers are vertically aligned, then center or shaft center is moved to this side, then shaft center is moved to this side. So, this is from literature I have picked up, and then we know this is a right thing. However, once a full film lubrication is developed, established from starting to real running condition, then we will know that this is the minimum film thickness. Again, I am talking about a steady state film thickness, and when we come to the dynamic film thickness, then this will not work. Particularly squeeze film lubrication and engine bearing, we need to solve dynamic loaded. That means there will be continuously changing, each crank angle applied load will be different. Even the shaft speed may fluctuate to some extent, and sometimes even the sleeve also rotates. So then we need to really think about dynamic loaded bearings, and here what we are talking about is steady loaded bearings only. And what has been mentioned here, at any rotation, you can see here theta is equal to 0. Of course, this is what we need to calculate, where the theta should be equal to 0. Sometimes people say theta should be 0 at the vertical or here, that's not correct. When you talk about xy coordinate, it's okay, but when you talk about r theta coordinates, then it's not okay. And here what we are talking, the r theta in this case, so theta is 0, and this has to be defined from attitude angle. Again, attitude angle is not being given to us. We need to figure out what will be the uh, geometry and what will be the establishment of eccentricity ratio and then attitude angle by solving the equation. So that way we do not have many data. Initially what we know only that applied load and rotating speed and maybe oil viscosity, but what will be the real attitude angle, what will be the eccentricity ratio, what will be film minimum film thickness, what will be maximum pressure, that will come only through the solution and solving the Reynolds equation or maybe say similar kind of equations. And then here what particularly we recommend, and even now from my understanding, this phi attitude angle has to be lesser than 45 degree. It is interesting to note applied load and then what bearing is sustaining load, it is some angle, and there is a phi angle. That means applied load is very high, then only the attitude angle will approach to 0. If applied load is a lesser, then this is a what this hydrodynamic can generate, then phi will be on higher side. And again we are saying phi should be lesser than 45 degree, because the system becomes unstable. Applied load is only 5 Newton, and what we say hydrodynamic firm generation can be 100 Newton. In the situation, naturally phi value will be very high and it becomes unstable, and that's again we have a different kind of problem. We need to solve those kind of problem related to the instability of the general bearing. That's also possible. However, for a starting purpose, we are talking only steady state, well established, no fluctuation in the shaft speed, no fluctuation of the load, and then again it is a well controlled phi is a lesser than 45 degree. In the situation, whatever you are going to discuss, that will work. Now here the way again we are saying hydrodynamic film generation is a self-acting. Now here the because of the rotation, the film is getting generated. Of course, as I say that initially we need to provide some sort of source from where the lubricant can be supplied, but major action is a self-acting, which is the beauty of the hydrodynamic lubrication, that it generates a pressure its own because of the rotating speed. And then it also creates a wedge. If you look at here in this shaft and the bearing configuration, we are not creating any wedge as such, but this wedge action is being created by its own. So that is a self-acting, right? So this is very important that system really do necessary thing for the sustaining the load. So this is important. And then after generating this wedge action, it is also stable and stabilizing the film thickness, so that is maintaining the film thickness, which is important. However, it requires really viscous drag. That's a major thing, that it really requires a oil viscosity, and we need to think about how oil viscosity really helps to develop a film thickness. That's important to consider it. And we know very well that viscosity is a simple internal friction among the fluid molecules, is a resistance basically, and higher viscosity number means a thicker oil. If I use a word SA10 as a one lubricant, now I say SA20, naturally viscosity of the 20 SA20 will be more than 10. Now if I say SA30, naturally the viscosity of lubricant will be more than 20 and 10. So as a higher number, we move on a higher number, viscosity will be on a higher side, or oil will be viscous or thicker. Now coming to the viscosity point again, but we say that here we, as I mentioned earlier, we require the boundary additives to be mixed, so that asperities, even in case they are trying to touch, they glide, they really slip and they become a slippery surface. While in thick lubrication we are able to separate this. Naturally, when we talk about the friction force, we need to see that how do we calculate friction force. There are a number of theories. Simplest is that think about what is the shear stress in a liquid and multiply with the area. And we assume that if the Newtonian fluid, naturally the Newtonian fluid, the shear stress can be given as a viscosity into velocity divided by separation. That's a separation over here. That's what we are saying, H separation. And here it has been shown in a much different manner. That's the same thing. H has been shown here, velocity has been shown here, area has been shown here. So this is what we can calculate the coefficient of friction from this angle. Now if instead of going for the straight surface, planar surfaces, we are talking about the journal bearing case. Naturally, in the situation we need to think about area. Area will be pi dl, and we know that d is equal to d of the shaft diameter is a 2 into radius of the shaft diameter, or journal shaft journal we are using synonymously, and then here it will be 2 into rj. Velocity, we know the pi dn, again it will be 2 pi rj into n. Here the h is not known to us. We can assume clearance, we can assume 50% of clearance, but more dominating when we started, they assume that two surfaces will be completely separated and the h will be equal to c. That's what it was mentioned here, and based on that the Petrov really developed equation of the coefficient of friction, which says the friction force divided by normal load. Friction force can be really given from this area. We have a friction force over here, and then we have in the normal area, or we say the load, which is really multiplied by projected area into pressure, that can be given. Only the difference between the area of the journal surface, where the lubricant layer will be intact on the surface, compared to this is a projected area, the pi is missing from this. So here it will be L into D, while when we talk about area and then this surface area of the journal surface, it will be pi dl. So it is not only LD, it's a pi that may multiply by 3.14 in addition to the projected area. Now if you substitute all this value, coefficient of friction can be given by this relation, and this is a well known Petrov equation, which what we say the coefficient of friction is proportional to the viscosity. That means more and more viscosity, more and more coefficient of friction, and more pressure. Here increasing load is going to reduce the friction. These are the quite contradictory what we already learned from the dry friction. Here as the pressure increases, as the load increases, coefficient of friction comes down. As the viscosity increases, and I mean the velocity increases, coefficient of friction will increase. As the clearance reduces, coefficient of friction decreases. As the shaft diameter increases, coefficient of friction increases. There are so many parameters. Naturally, many parameters will not be, the results in these days will not be the same, but at the beginning they did it. And when we do want to really use a machine learning or maybe say advanced mathematical modeling, we can take initial guess from these relations and then we can build on that. Now what we say, the friction coefficient of system is basically equal to fluid from friction coefficient. Initially we say coefficient of friction overall is basically coefficient of friction because of liquid, also because of the metal, and also in this situation one case we say the mu will be replaced by the B, right. If it can be equal to the only full fluid lubrication mechanism if the two members are equal and thus completely separated. When the two surfaces are completely separated, then assuming the coefficient of friction of system is equal to fluid from lubrication, that makes sense to us. That's right. But this is what is being mentioned over here, right. So these are the important aspects to learn. Now, one more thing comes, the viscosity is highly dependent on temperature. By changing the 10 degree of the lubricant temperature, viscosity reduces significantly. So, what are the relation available? Actually, we are trying to explore the literature, what is available, which can be utilized in a best manner. So, there are two relation, what we call a Vogel's relation, other one is a Vogel's relation, Walther's relation. One is related to the dynamic kinematic viscosity, other one is related to the dynamic viscosity, right. So in one case is the dynamic viscosity, other case is the kinematic viscosity, and here there were two parameters, two coefficients, two constant, while in this situation we have a three constants. So how do we do that? Now here suppose in this case viscosity is being given the different temperature 40 degree, 100 degree, 130 degree. That means we can really find out this relation also and we can find out this relation also. Only the drawback in the first relation is that this is for the dynamic viscosity, and for dynamic viscosity we cannot use directly Cst value, we need to convert into millipascal second. That will be required a kind of density of the lubricant. One more thing is that if the results are published and we want to really learn what is the really relation, because here it has been mentioned log log. Now when we write a log log, by default it is a base 10, but when you use a MATLAB, if you want to write log 10, then you need to write log 10. So from one compiler to other compiler, from one book to other book, it is slightly different. So that's why we always check first whatever the equation has been written, is it really what we are understanding is the same or something different. So for that purpose, now suppose in this case A and B also been published, so we can verify whatever we understand from equation, it is correct or not. So that's why I written simple MATLAB code. Here A has been initially defined something from here only. This is a 9.59, other is a 3.7. So we are substituting, and temperature particularly in this case we know that 40 degree and 100 degree centigrade, which can be utilized for the viscosity in this case. So here we are someone trying to figure out what will be the viscosity at the 40 degree, what will be viscosity at the 100 degree, and here when we use a E instead of in the 10, if I use E or if I use a log base 2, it will not satisfy. Only the log 10, or maybe say that when we are talking about the 10 power, then only the values 32.6 and 5.57 will come out. So this is kind of assurance, whatever we are picking up from literature, that is the right way. Many times, as I mentioned, some places it is written ln as a log E, but in MATLAB software log is a log E. So there is a need to really verify. Then comes the density, because I say dynamic viscosity, we really record the density. Again, density of the lubricant is varying from 860 to 900. Sometimes people can take 880 also. There is a possibility. But one point comes, then when the viscosity here is already defined 30, 16, 90, why do we really go with this relation? Why not I come to this relation directly? One more thing comes in a mind, then when we have already viscosity defined as 3 points, Why not we go ahead with directly curve fit equation? Why do we really require a Vogel's equation? Now we know the curve fit equations are available, and whichever gives a 99 point plus percent verification, I will go with that relation, and that can be a part of the algorithm itself. When I'm using the MATLAB as a program, I can directly type it. You use a curve fit method and it will be done, and we can provide this data. Why do I really require a separate equation? However, from literature point of view, we try to understand first whatever the relation was coined or maybe defined earlier, what is the validity? If I am trying to understand from curve fit method, I use that method, will that be more suitable or will have some sort of drawbacks? So for that purpose, what we did also, we took this as a x coordinate, and this the x as a temperature and y as a viscosity. Naturally, in case of the spindle oil we have used, but if I use a light machine oil, I use this one. If I use a heavy metals, I will use this kind of viscosity. Light machine, I will use this. So I have all the data now. I can really generate and figure out whether one curve fit equation is really helping or not. But one point, now here we have only 3 parameters, and we require a 3 we have a 3 values and we require a 3 parameters. That means if I solve the same equation for the next light machine oil, I have to resolve everything. For heavy machine, again I have to resolve everything. So there is a drawback in this. Now if we have many data, then we can really go ahead with the generalization, because generalization is very important. Whatever the model we use, if it is generalized only with changing 1 or 2 parameter, it makes a lot of sense to us. However, it has a 3 coefficient and have only 3 values. For every oil it will need to be changed. So there is a what we say, every time we need to do a recalculation. For that purpose, I am just trying to show that. Now in this case again 30 degree, 60 degree, 100 degree, and we use a curve fit equation, and then MATLAB has a curve fit with only 2 terms and then 2 coefficients. If you want more, then they will add a 2 more. That means 2 or 4 or 6 something. That way we can do it. But if this relation itself fits a 3 value, it gives a good results. Even though if it can be, we can say it is a overfit, fine for us for time being, because in lecture 23 onward we will be learning what is the overfitting and how do we solve that overfitting, how do we really purify or minimize the noise of measurement itself. For time being, we are trying to say yes, there is a curve fit, 2 points, and we are trying to learn. It is giving 99.997, but the r square value is a 0.9997. It's a very good curve fit pattern, and we are able to see as also points, whichever 3 points have been given to us, they are falling on this curve. So this is a fine for us, and this relation can be utilized. However, this also indicates that we can improve our understanding from this. Question comes, why not I choose K as a viscosity itself? Now I know that 6.3 has been given. Now I can choose viscosity directly in this term, and viscosity at the 60 degree, and modify. We know that with the temperature, with an increase in the temperature, viscosity is going to decrease. That means value of the B will be negative. I can choose -1 also, or some other parameters, and that will really improve our thinking. So that's what we have given here. Now here in this case situation, and I have assumed and 60, and here theta has been selected from me by me as a 60 degree. Now this also creates a one impression that T, which is here, it has to be in centigrade, it should not be in Kelvin. So this is an understanding when we are trying to explore the relation, that our understanding improves significantly. First thing is that I don't have to do this equation again and again. Whatever the viscosity has been given, I can choose at the mid value directly there, and whatever the temperature has been given, I can choose select T minus the temperature. So it is satisfying it. Now this there is a value B, because it has to decrease, actually that there is a negative sign has to come here, right? So it is easier. Now instead of 3 constant, I have only 1 constant, but instead of 3 I have only 1. That means I solve 2 without really doing much effort. After that, viscosity is given and it can be solved. Using this kind of relation also is easier, and you can see here, of course, we have not gone for much higher accuracy. You can see here when we choose this, so even though we have selected 6.3 initially, Crawford method gives around 6.4 with a lower and upper bound, and then again our value comes out 0.997. Here I have selected only one, and then try to give the relation from that point of view. So instead of using this equation A and B of the curve fit, I can directly use my own algorithm, which can be given far better results compared to this. And what we say, instead of three constants, we have reduced to one. We know very well that when there is only one parameters is a constant to be figured out, solving equation is much faster compared to the solving three parameter equations. Now coming back to the pressure mechanism, so why the pressure is generated, we say if there is a wedge action. So initially there is no wedge, two plates are parallel, now there is a wedge. Now because of the wedge, or maybe alpha has been given, there is a tilt angle, and then we say there is a velocity v here. Naturally whatever the inflow of the lubricant, that cannot really come out easily, because velocity is similar. So velocity of this surface is a constant, where this surface is constant, velocity is not changing, and maximum velocity of lubricant can be only the velocity of the upper surface or relative velocity. So that will be maximum. So then only one way comes, if there is a negative pressure generation at the entrance and positive pressure generation at the exit, then only the this mass conservation equation, obviously the fluid equation, will be satisfied, or continuity equation will be satisfied. And that's what we say, positive pressure gradient at the exit and negative pressure gradient at the entrance. That means there is a negative pressure here, there is a positive pressure here, and this is what we wanted to generate a pressure to elevate or to levitate the shaft. And overall it can be given in this manner. You can see here, even though dashed line velocity has been given, now because of the pressure generation or negative direction, overall flow rate will be retarded, will be reduced, while in this case because of the pressure, positive pressure, and overall flow rate will increase. So at the mid we are saying the pressure will be same. Now because of the tilt, initially at the entrance pressure is going to negative side, while the exit pressure is going on positive side. We know very well that at the entrance, even the pressure is negative, liquid lubricant cannot sustain liquid negative pressure. So there the cavitation will start. Many times we say cavitation is bad, but well controlled cavitation is good, where we can really feed the lubricant oil proper manner. That means instead of going for the high pressure pump, I can go with a very low pressure pump, slightly more than the ambient pressure, or even the ambient pressure, because of the some sort of gravity if I provide, that will help. So if we provide a pressure input here, I'll show you in the next slide in a figurative manner that how do we do it. So this is a good learning. I can really reduce a pump pressure, and still I get a good lubricant layer in a hydrodynamic lubrication mechanism. Now overall this equation can be developed by solving the we can start with elemental analysis, balance, and try to rearrange, and this equation can come in this form, that something like pressure generation x direction, pressure generation is z direction. Here we are assuming y direction is a film thickness direction, right? And then there is a velocity, relative velocity, velocity u2 of the one surface, u1 is other surface, then velocity, and again assuming the squeezing action, velocity of the surface 1, surface 2, then in the perpendicular direction, velocity of the surface 1 and surface 2 can be given in this relation. However, this has been described well in my book in chapter 3. Again, I am not going in detail about this. Sometimes we say instead of u2 minus u1, we directly write u, and w2 minus w1 we write directly w, right? So it's a relative velocity. Now this can be solved in different manner, numerical method of some sort of assumption, and then only thing comes, whatever we do, we are taking some assumption. Now in this case, reason being, I can assume as a eta as a function of the temperature and the pressure, because pressure viscosity effect will come, and temperature also. Now Another thing is that if it is, then it will be highly non-linear. Sometimes we assume viscosity is a constant for time being. It's an isothermal case. Viscosity is not going to change with the temperature, and there is no change in the temperature because of this. However, in reality it will not be. So whatever the literature has solved equation, there are some assumptions, and then finally some correction factor of safety were accounted. Now when we are talking about the machine learning, quite possible we can take initially very simple model from this and can build on that, and maybe think about the reinforcement learning that can be utilized for this purpose. Now what we say here, optimal hydrodynamic lubrication is achieved when relatively moving surfaces are adequately separated, or we can say separated by substantial lubricant film with a friction force depending on the viscosity of the lubricant. If that is the case, then again decreasing viscosity will be a trend, will be really required. Otherwise, we can go ahead with and then the boundary additives along with this and using thinner oil. Now, as I mentioned that I will show in how the lubrication happens in a real film lubrication. So here we use some sort of acrylic material bearing to see the cavitation effect into the hydrodynamic bearing. This is the leak the bath where from where the liquid lubricant is extracted. There is a filter mechanism, there is a pumping mechanism here, and then we are trying to utilize with some sort of we have some sort of temperature sensors also and pressure gauge, which we can really can see the differences also. So this is was completely transparent surface, so we could see easily what is happening inside the bearing, and this is a word cavitation effect. You can see here the shaft is rotating in this direction. Full film lubrication doesn't happen at this level also, and there is a some sort of the gap, there is no liquid lubricant, and these are the streamers. We are showing the liquid lubricant is there, but there are air cavities also. To solving this equation, again we can do it that way. Mass conservation principles or conditions can be utilized for this purpose. However, just for the purpose of the scientific understanding, we are showing this figure, and we are showing that there is a cavitation in this. So this is what came from a Reynolds equation, and then he solved it and then figure out that oil hole position should be changed, and this is where we are trying to show if oil hole position is in this zone, I am showing with the red color, in this zone, then oil will come in a reverse direction and hydrodynamic action will be missed to some extent. However, if we are providing a lubricant from this surface or this portion, that will be advantageous. So making oil hole, oil groove, which place at which portion of the bearing is really important. If we make oil hole in this portion, then it is advantageous. That's why we are trying to solve this kind of problems. Overall results are in favorable thing. Again, as I mentioned that we are in these days, there is a trend from a thick to thin lubrication, or I can use a word hydrodynamic to the mixed lubrication. So we have a lot of importance for the mixed lubrication. Reason being, we don't want complete hydrodynamic, because we know the viscosity will try to reduce will increase the friction. That is important, and then we don't want it to increase the friction, even though it try to reduce the wear coefficients or maybe the wear rate, but increases the friction. We want balance both, that we don't want the wear and we don't want the friction also. Again, even though we can develop a full film thickness, but at the beginning and the end, again there will be wear. So that's why we really require lubricant additives or slippery surface or maybe to be made on asperities, so that overall friction is lesser, overall wear is also lesser side. So that's why we say that the thin lubrication is far more complex, and then we really required surface roughness level knowledge, which we have already covered, and this asperities should be covered by lubricant layer. And we say that liquid lubricant has some limitation in the load carrying capacity is slightly lesser compared to the solid lubricant. However, solid lubricant and coating have one of the major issue, that they cannot dissipate the heat. So there are some advantages with a liquid lubricant, some advantages with a solid lubricant, and that's why we say better we go ahead with mixed lubrication. We connect both. We want liquid, we want solid, or maybe say boundary additives. So overall results are in our favor, or maybe overall favorable to the tribology society. Now that's why, and this because we are talking of the complex phenomena, we say term addition, lubricant, sliding friction, starting friction, temperature, all things will be important, and that's why the first 8 lectures were given on this topic. When we are talking about the tribopier, everything is important, and if we lack understanding of any topic, naturally we will not be able to achieve the optimum results for ourselves. Now, one of the major issue comes in IC engine. You can see compare 1960 number of vehicles, number of cars, number of trucks, and overall vehicles. Compared to that, in 2019, it was almost a 12 times number of vehicles. So pollution level is a one thing, but consumption of the petrol is increased significantly. And then most of the IC engine tribe surfaces are coming as a tribo surfaces. You talk about the wall train, talk about the piston ring package, engine bearings, talk about the gears, talk about the rolling element bearings which we are utilize, or even we talk about the cam follower mechanism. They all are the tribo surfaces or tribo interfaces, and we need to reduce friction at those surfaces. Again, you can see here what we are talking, the friction. As the hydrodynamic lubrication, friction is increasing. So we are not worried about, or we are not interested in hydrodynamic lubrication. We are interested in thin lubrication, something like in this layer, or maybe say the curve should go in a straight line. This it should not increase, it should not go in this manner. So this is rejected and this is accepted for us, and that's why we need to really do hydrodynamic lubrication in a manner so that it really supports other lubrication mechanism. So overall we are interested in mixed lubrication and we want very good results for ourselves. Now one quick I'll give you the some sort of a lecture that how do we get a quick results from hydrodynamic bearings or hydrodynamic lubrication theory or Reynolds equation. This Reynolds equation we have shown earlier, and then we say quite possible W is not existing tangential direction when we talk about the sleeve bearings or maybe the general bearing. This W doesn't exist, and assuming that VH minus V0 is also 0, and then U is only existing. That's what with the Reynolds equation can be reduced. So again there are some assumption and we have completed the sub assumption. Again because there is a trend of reducing the size of the components, so more and more the short bearings have been now in common. The bearing diameter can be bigger but length has to be smaller, and that has been done. So in the situation what will happen, pressure gradient in Z direction, this is the Z direction, pressure gradient in that direction is much higher compared to x direction. So if this is a 5 to 10%, we will try to simplify equation in this manner. Now this is kind of the easy to solve relation compared to the two dimensional. And in this case particularly we can give a film thickness. This is a film thickness. In the case any place film thickness can be given something like that. This is says a clearance plus E cos theta, and we know that cos theta will turn out to be 180 degree here, that will be the negative. So minimum film thickness will turn out to be C minus E, and E this eccentricity, and we often normalize eccentricity and we say eccentricity ratio, that is E by C, right. So this is done. Another when we give x coordinate in terms of r theta, so once we do this kind of thing we can simplify for the relation and we can integrate. There are integration there are constant c1 c2. This can be solved using the boundary condition. We know the shaft outer surface or maybe say bearing edges pressure has to be 0 or ambient pressure. So that way we can solve this equation. When you use this equation we can really get the pressure directly in terms of omega rotational speed, in terms of viscosity, in terms of clearance, in terms of length, in terms of epsilon also, that can be easily achieved. Now sometime we want to know maximum pressure. So naturally here only one variable is the theta, so then we can differentiate equate to 0 because of the gradient, and then we try to solve it, and then we can figure out also what will be the location of the maximum pressure. Once the location is known, we can substitute and then we can find out the P maximum. Now what is interesting to note, applied load is in this direction and maximum pressure is not just opposite here, it's some coming somewhere here. Another thing, minimum film thickness is coming somewhere else. So often people feel that applied load wherever pressure will be opposite to that. That's not happening in a hydrodynamic bearing. Similarly, film thickness, it is a different place. Theta is a slightly different or away from the P max. So it's not the same. So this is important, particularly people who do not have these concepts, they commit a mistake even though they try to do machine learning algorithm, then they are not able to solve this and then they will commit more mistakes. So what we say generally, the bearing design is an inverse problem. It's not direct problem. Reason being, we need to really find out eccentricity ratio and attitude angle from given weight and speed. But if you look at, pressure is given in terms of eccentricity ratio. Theta max is given and the maximum pressure location is given in terms of epsilon, but epsilon is not known to us. So these are the inverse problem. We need to do iteration, and when we do iteration, naturally it will computational efficiency will come into the picture, how fast we are able to convert the results. So for that purpose, generally we solved this load equation, load in x direction, load in y direction, try to find out the expressions. We can do a numerical solution also, but there is some sort of a Sommerfeld table available for integration. And here what we are using the boundary condition. Here we are using the 0 to 2, 0 to pi as a boundary condition. What's the meaning of that? I'll just try to explain that what we are saying, the pressure start from here and ends over here. That is a word assumption. Pressure generation will start from here and this is a divergence zone. There will not be pressure here, that will not be counted a pressure. So this is another assumption, and as I say that most of the time we are solving using a number of assumption may not be valid for every situation. So here what we are saying, the Wx, Wy and W can be given. You can see here W again in terms of the eccentricity ratio, which is not known to us. We are knowing what is the W, but eccentricity ratio is not known to us. So it's the inverse problem. Another one is the attitude angle, also it is not known to us, and then is again in terms of the eccentricity ratio. So we need to solve this problem, and it says the most currently available numerical algorithm perform general bearing analysis by assumed eccentricity ratio and attitude angle. Without that, we will not be able to solve problems. And we say in this situation we use initial estimation of eccentricity ratio. Nothing is known. We many times we start with a 0.5 as eccentricity ratio, attitude angle as a 25 degree when you start, and then we need to come up with a feedback loop system, and then we have a feedback loop or iterative strategies to obtain the right load and speed till we do come up with a specific speed or right load condition. Our solution will not be able to converge, and it will convergence maybe iteration will be continue. So with this I say thank you. This bearing design will be covered in the next lecture, which is the lecture 10. Thank you.